Welcome to Forrester University's Constant Flow, All You Need to Know webinar. This webinar is free for you thanks to our sponsor, Thirsty Duck LP. Our presenter today is John Moody from Thirsty Duck LP. I'll be introducing John in just a minute, but as we wait for everyone to come online, I'll cover a few housekeeping items. My name is Haley Hogan, and I am the Product Marketing Manager at Forrester University. I'll be your moderator today, behind the scenes, taking your questions for John throughout the broadcast so he may address them during our question and answer session at the end. Today's webinar is scheduled for approximately 1 hour with a 15 to 20 minute question and answer session to follow. Those who stay to the end are eligible for a completion certificate towards 1 PDH and 0.1 CEU credits in states where applicable. These certificates will be emailed to those who qualify. If you have joined us in a group with additional attendees who have registered, please send your attendance form to Zach after the webinar at ztrafney@forrester.net. If you have joined us in a group with additional attendees who have not yet registered but would like to receive CEU PDH credits, please contact Zach after the webinar and he'll get your attendees registered. Today's webinar is interactive and we encourage you to ask questions throughout. You may do so by entering a question in the question box and clicking send. These will come to me during the session and I will pass these on to John to address during today's question and answer session. If we run out of time today, we'll respond to any remaining questions via email. You may also check your audio here. If you do not have audio, please enter a question in the question box and I will try and help you. There are a few best practices that we recommend for an enjoyable experience. First, we recommend jotting down this website and web ID, so if we lose you, you can get back in quickly. Second, we recommend using a high-speed internet connection with all other windows and programs closed to avoid any audio or visual lag. Third, we recommend turning off or setting aside all cell phones to avoid any buzzing or static with the audio. And finally, we are live tweeting this webinar. You can join the conversation on Twitter by following us at ForresterU and including hashtag ConstantFlow in your tweets. We'll be following your comments and questions during the webinar as well as after. And with that, I'd like to introduce today's speaker. John Moody is the Chief Operating Officer of Thirsty Duck LP and the inventor of the Thirsty Duck ER series Floating Outlet and Skimmer. Moody holds a bachelor's degree in civil engineering from the University of Florida and has over 25 years of experience in the field of civil engineering, including design, project management, and research and development. His specialty area of practice is commercial and residential land development with a focus on stormwater, hydrology, and hydraulics. And with that, I'll pass the baton off to John, and John will begin today's presentation.
Well, thank you, Haley. I see that we have over 400 attendees online already, and I'm told that there will be over 800 before we're done today, and that's quite an honor. I was never expecting this much turnout for today's webinar. I'd like to take a minute to thank Haley and her team at Forrester Media for working so closely with myself and the staff here at Thirsty Duck to make this webinar possible. It was a lot more work than we ever thought when we started this back in December. So, over the past year, I'm sure most of you have seen our magazine ads which challenge the traditional notion that when it comes to stormwater detention, the only solution is more volume. Since most stormwater systems are required to operate passively, the only devices that we've had at our disposal to control outflow are weirs and orifices, both of which produce varying flow rates as water levels rise and fall. Today I hope to unlock some of the mystery around the idea of constant flow and how this new tool can be used to do things which were never possible in the stormwater world up until now. So today I'll answer the following questions for you regarding the subject of constant flow. First, why constant flow? And then what is a buoyant flow regulator? How is it that these things work? How do I model them? And then what are the good and not so good applications for this technology? So let's get started. So why constant flow? The volume stored in any stormwater detention system is the difference between what flows in the system over time minus what leaves the system over time. You know these two curves as the inflow hydrograph and the outflow hydrograph. From calculus, it's the area between these two curves which represents the volume stored. When traditional static weirs and orifices are employed as the method of flow control, the peak discharge rate from the system is only achieved for one instantaneous point in time. This happens when there is the most head acting over the weir or orifice, and that happens when the volume of storage is completely full. If it's possible to achieve the peak discharge rate earlier in the inflow and then maintain that rate across the duration of the inflow, the area between the inflow hydrograph and the outflow hydrograph is minimized, and a significant amount of storage volume is no longer required in the system. So, the flow delivered by the old-fashioned orifice, which is what we've all used in the past to control outflow from stormwater detention systems, is a function of the area of the opening of the orifice and the head acting on it. Here you can see that as the depth of the water or head over the orifice increases, the flow rate also increases. However, if we somehow had the ability to make that hole move up and down with the water surface, such that it was always at a fixed depth below the water surface, the head acting on the hole would remain constant, and thus the flow produced would also be a constant. So how is it that we make the hole move? Well, that's where buoyant flow regulators come in. A buoyant flow regulator is a device which creates a constant or nearly constant head condition by suspending an orifice from a float such that the orifice is always located at a fixed distance below the water surface. And there are three principal types of buoyant flow regulators which are defined by the means by which they get their motion. These three types are 1, the flexible hose type, 2, the expanding conduit or bellows type, and last but not least, the concentric tube type. My company, Thirsty Duck, makes both the expanding conduit and concentric tube kinds of these devices. The simplest and oldest version of buoyant flow regulator technology is the flexible hose type. It is most commonly used in temporary construction stormwater or sediment control ponds, and the first known use of such a device was the Whippany Swamp Stormwater Demonstration Project in the state of New Jersey. Back during the early 90s, in order to better control the recovery of the extended detention volume, Dr. George Guo of Rutgers University equipped the outlet with a homemade device he called the floating riser. The floating riser was fashioned from PVC pipe and connected to the outlet with a piece of flexible tubing similar to the drain hose found on the back of your washing machine. Later, in the mid to late 90s, the technology was better refined and brought to market by Jesse Warren Faircloth, a North Carolina stormwater permit reviewer and sediment control inspector. His device, the Faircloth skimmer, has been employed in thousands of temporary sediment basins and is available on the market today. I'm sure that many of you from North and South Carolina, Tennessee, and Pennsylvania have seen or may have experience using this device. Like Dr. Guo's floating riser, the Faircloth skimmer is constructed from PVC pipe and consists of a float which supports a tube that has an orifice situated at its upper end. The orifice is located behind a screen which keeps out floating debris which might clog the opening. And a flexible hose located near the lower end of the tube allows the Faircloth skimmer to move up and down with the water surface as the pond fills and drains. The next type of buoyant flow regulator to hit the market was the expanding conduit or bellows type. It was invented by Adam Fulton of Bellingham, Washington, and it consists of a flow restrictor, or orifice if you will, which is suspended from a float and connected to the outlet with an expanding tube known as the bellows. As the water surface rises, the float extends the bellows in the water column and likewise allows it to contract as the water surface falls. The Thirsty Duck TDP series buoyant flow regulator is an example of this type of device. Here you can see a closer view of the inside of a bellows type buoyant flow regulator, which shows how the orifice or flow restrictor is suspended below the float such that it is always at a fixed distance below the water surface so as to create a constant head condition. The newest type of buoyant flow regulator is the concentric tube type, of which yours truly is the inventor. This type of buoyant flow regulator works by suspending a flow restricting tube inside a stationary tube which is connected to the outlet. The floating tube has a larger dimension at its bottom than at its top, such that the area or the gap between the floating and stationary tubes is smaller at the bottom, Since the gap moves up and down as the water levels both rise and fall, it's always located at a fixed distance from the water surface and operates at constant head. In some configurations of this device, water is also allowed to pass through an orifice located inside the tube at its upper end. Like the gap formed between the two tubes, the orifice at the upper end is always at a fixed distance below the water surface and also operates at constant head. The next series of slides should help you better illustrate this concept. So here's the traditional stormwater outlet riser, which most of you are familiar with. The riser is a stationary tube which is connected to the outlet, and as the water levels rise over the top, head increases, and likewise the flow to the outlet also increases. When a floating flow-restricting tube is placed inside the stationary tube or riser, the area of flow is now reduced to the area between the two tubes at its smallest point, and in some configurations through an orifice located in the center of the upper end of the tube as well. The Thirsty Duck ER series buoyant flow regulator is an example of this type of device. So here's a little trivia question for you. Although it's I that lay claims to the invention of the concentric tube type buoyant flow regulator, I'm actually not the first person to think of this concept. When do you think the first concentric tube type buoyant flow regulator was invented? A, 2004, B, 1999, C, 2009, D, 1902, or E, 1955?
All right, so please put your vote in. The question is, when was the first concentric tube type buoyant flow regulator invented? 2004, 1999, 2009, 1902, or 1955? And I will tally up the results and share those with everyone. All right, and let's see. 40% say 1902. 38% say 1955, 15% say 1999, 5% say 2004, and 3% say 2009.
Well, the correct answer is D, 1902. Way back in 1902, a gentleman by the name of C.C. Carlisle out in the state of Wyoming patented a device he called the self-adjusting Weir. It was intended to meter out water from irrigation canals such that the farmer or rancher always received the same amount of flow of water, regardless of whether the water level in the canal was high or low. Similar to my invention, the device was fashioned from one stationary tube connected to the outlet and one moving tube suspended from a float. The key difference between this invention and mine is that water is only allowed to pass through the center of the moving or floating tube. The flow of water is not restricted by the gap between the two tubes. In fact, Mr. Carlisle had proposed a watertight, frictionless, as he called it, seal between the two tubes, formed by a gland containing a fluid which would be much denser than water. Since the fluid in the gland was heavier than water, it would prevent water from passing through it, but there are a couple problems with this theory. First, the fluid he proposed to fill the gland with was mercury. Why don't some of you try explaining to your local regulatory agency that you want to put a mercury-containing device into a stormwater system? Second, as the walls of the floating tube move up and down inside the mercury, the amount of mercury which is displaced is constantly changing. This changes the buoyancy of the tubes, so therefore the device could not actually float at a constant depth below the water surface and therefore would not actually deliver a truly constant flow. At Thirsty Duck, we make the concentric tube type regulator in 3 different configurations. The first is the simplest and most easiest to understand, and it's known as the single restriction configuration. In this configuration, flow is only restricted by the size of the gap between the floating tube and the stationary tube, and no flow passes through the center of the floating tube. The second is known as the dual restriction configuration, and in this configuration, an orifice is located in the center of the upper end of the floating tube, such that the flow is restricted both around the floating tube and through the floating tube. The third is known as the hybrid configuration, and in this arrangement, flow is restricted through an orifice located inside the upper end of the tube, and also by the gap between the two tubes. However, in the hybrid configuration, the floating tube has the same dimension at both its top and bottom. This forces the restriction to the top of the stationary tube rather than the bottom of the floating tube. As you can see in the animation on the screen, the head acting on the orifice in the center of the tube remains constant, while the head acting on the gap between the tubes is increasing as the water level rises. And I'll talk to you a little bit more about why this configuration exists later in the presentation. So now that we understand a little bit about the basic hydraulic principles by which these devices operate, let's take a look at the forces that govern how they move and where they float in the water. I'm going to focus on the two types of flow regulators that Thirsty Duck manufactures for this next part of the discussion. In the ideal world, the Bellows type buoyant flow regulator will produce perfectly constant flow. However, that's not completely true because what is ideal is not exactly real. In the ideal world, the only forces which would have to be balanced to achieve a constant head condition would be the upward acting force of buoyancy countered by the downward acting weight of the device. The problem is that extending the bellows is much like lifting a chain. When a chain is lifted from the floor, the amount of weight being lifted is directly proportional to the number of links you are holding up. As the bellows is extended, the amount of weight being lifted by the float is also increases. And as it nears the limit of its vertical rise, it also begins to stretch a little bit. This stretching creates exponentially increasing tension, which also acts downward against the upward force of buoyancy. Since the amount of downward acting forces are always increasing as the flow regulator rises, it causes the float to sink a little lower in the water, which means the ideal constant head condition is not truly achieved. Also, the force of drag can be a factor. When an object moves through the water, the force of drag acts in the direction opposite its motion. The good news about drag is that it's a function of the square of the moving object's velocity. And since the vertical velocity of the water surface in a stormwater detention system is typically very, very slow, the force of drag is nominal and can pretty much be ignored. So this is the typical rating curve or flow versus elevation relationship for a Bellows type buoyant flow regulator. As you can see, the flow rate increases slightly with increasing water surface elevation due to both the increasing amount of weight which must be supported by the float and the tension which develops in the bellows when it begins to stretch near the top of its extension. So it's not perfectly constant, but it's still close enough to achieve really good results. The forces which act on a concentric tube type buoyant flow regulator are similar yet different from the Bellows type. For this type of device, the upward acting force of buoyancy must be balanced with the downward acting forces of weight, impulse, and drag. Unlike the Bellows type, the forces acting on a concentric tube type flow regulator remain constant, and the device will actually float at a fixed depth of submergence, creating truly constant head condition and truly constant flow. Since the floating tube is rigid, the weight being lifted by the float is always the same. As with the Bellows type, since water levels in stormwater detention systems rise and fall relatively slowly, the force of drag can typically be ignored. But the real trick to analyzing the total downward force acting on the device is being able to calculate the force of the impulse of the flowing water against the lower portion of the floating tube. Some of you may have a vague recollection of the impulse momentum theory from your college fluid mechanics course, and I will tell you it's a pretty complicated exercise to actually calculate this force, but I'll spare you that agony for the rest of this presentation. So now that we have a basic understanding about how buoyant flow regulators work, let's talk about how you can calculate the flow rate through these things and how you go about developing the rating curve or flow rate versus elevation relationship for each of them. The good news is you only need to know two equations, unlike analyzing all the forces that act on these things. Oops. The great news is that the point of these devices is that the head remains constant or nearly constant. In the case of the Bellows type, the math is actually very, very simple. The most important thing you need to know is when to use each equation. As the depth of water increases over the edge of a horizontally oriented orifice, the flow starts as Weir flow and then transitions to Orifice flow. The depth at which Weir flow transitions to orifice flow is known as the transition head. You can calculate the transition head by setting the Weir equation equal to the orifice equation and then solving for the head, h. In this cross-section of a Bellows type buoyant flow regulator, you can see that when the depth of the water is below the transition head, the Weir equation applies, and conversely, the orifice equation applies when the depth of the water is greater than the transition head. The same is true for the concentric tube type. However, there are more edges for which the transition head must be determined. In the case of a dual restriction configuration, as shown here, it is necessary to determine the transition head for each of the openings or paths of flow through the device. When calculating the flow rate through a concentric tube type buoyant flow regulator, it is assumed that water always first fills the space between the tubes before it discharges through the orifice at the upper end of the floating tube. The other trick to calculating the flow rate through these things is knowing how to measure head. Buoyant flow regulators can only produce constant flow when they operate in a free discharge condition. When free discharge conditions exist, head is always measured from the elevation of the flow restriction to the upstream water surface. Notwithstanding the effects of bellows weight and tension, head is always a constant in a free discharge condition. Unfortunately, and especially down here in Florida, when submerged outlet conditions exist, meaning the downstream water surface elevation is higher than the elevation of the flow restrictor or orifice, head is always measured between the downstream water surface and the upstream water surface. When this condition exists, the buoyant flow regulator functions exactly like any other traditional Weir or orifice and produces a flow rate which varies with upstream and downstream water surface elevation. Being able to identify when free discharge and submerged outlet conditions exist is even more important when calculating the flow rate through a concentric tube type device. There are three possible cases which can exist as a concentric tube type buoyant flow regulator rises and falls. The first case is the simplest and the best. A free discharge exists on all openings. This condition exists so long as the downstream water surface is always below the bottom of the floating or moving tube. The second case is that a free discharge exists at the orifice located in the upper end of the floating tube, but a submerged outlet condition exists in the gap between the stationary tube and the lower end of the floating tube. The third and final case is that the submerged outlet conditions exist at the orifice located in the upper end of the floating tube and the gap between the stationary tube and the lower end of the floating tube. So let me better illustrate these. Here on this slide we have case 1 flow. And here a free discharge exists at all of the openings or points of restriction to the flow. For this case, the head acting on the opening is measured from the point of flow restriction to the upstream water surface. This is an illustration of the second case, where the orifice in the upper end of the floating tube is operating in a free discharge condition, while the restriction to flow at the lower end of the tube is in a submerged condition. For this case, the head on the upper restriction remains constant and is measured from the flow restriction to the upstream water surface, while the head acting on the lower restriction is measured from the downstream water surface to the upstream water surface. Therefore, as the floating tube rises, the head acting on the lower restriction is constantly increasing. But note that once the lower restriction rises above the tailwater, a free discharge condition will be created, and the second case now becomes the first. For the third case, both the upper and lower restrictions are submerged and head is measured from the downstream water surface to the upstream water surface. You'll note that for this case, the head acting on the upper restriction is exactly the same as the head acting on the lower restriction. If you can visualize the floating tube beginning to rise, you can see that once the upper restriction in the center of the floating tube rises above the tailwater, the third case then becomes the second case. So let's see how many of you are paying attention out there. Here's another trivia question for you. Which flow case, case 1, 2, or 3, would it be when water is flowing backwards through a concentric tube type buoyant flow regulator? A, case 1, B, case 2, C, case 3, D, none of the above, or E, all of the above.
All right, and just let us know what you think. Which flow case is backwards or reverse flow through a concentric tube type? Is it case 1, case 2, case 3, none, or all of them? And just click on the screen with your vote and we will get those in here and I'll tally them up and share the results with everyone. Let us know what you think. And I will close the poll and share the results with everyone. All right, and there's a tie for 37% for none of the above and for case 3. 15% say case 2, 9% say all of the above, and 3% say case 1. So do you want to let us know what the answer is?
Sure. Well, the answer is case 3. As illustrated here, when the tailwater elevation is higher than the headwater and the flow is backwards, both the upper and lower restrictions are submerged, which is the definition of case 3. So why the 3 separate cases? These 3 separate cases of free discharge and submerged outlet conditions are the reason for the 3 different configurations of the concentric tube type: the single restriction, the dual restriction, and the hybrid. The single restriction configuration, shown on the left, is typically best suited for use when tailwater conditions are low, such that as the floating tube rises, a free discharge condition will develop as the lower flow restriction rises above the tailwater elevation. In the dual restriction configuration, which is shown in the center, that's best suited for moderate tailwater conditions, where case 2 flow can be established and then potentially transition to case 1 as the floating tube rises, such that eventually both restrictions will be able to operate in a free discharge condition. And last, the hybrid configuration, which is the most popular configuration down here in Florida, which is shown on the right, that's best suited for high tailwater conditions. Since there's no lower flow restriction in the hybrid configuration, all of its restrictions can remain above the tailwater and operate at free discharge. We call it the hybrid because the inner restriction is producing constant flow, yet the outer restriction is producing increasing flow with increasing water surface elevation, since the point of restriction is fixed at the top of the stationary tube. So the other thing that you need to know to calculate flow 2 is what is the proper coefficient of discharge to apply to the Weir and the Orifice equations. Thirsty Duck has done a lot of lab testing to determine the appropriate coefficients, and believe it or not, to our delight, we found that the actual coefficients correlate very well to values commonly published in the textbooks. For all Thirsty Duck models, the coefficient of discharge for Weir flow was determined in the laboratory to be approximately 3.2. and this is a commonly published textbook value for broad-crested weirs. For our models TDP 184 and TDP 248, which are Bellows type buoyant flow regulators, the orifice coefficients were found to be 0.55 and 0.62. These values are also very close to published textbook values. For the concentric tube type, or ER series, the Weir coefficient was determined to be 3.2, again correlating very well with textbook values, and the inner restriction was found to have an orifice coefficient of 0.62, again correlates very well with textbook values. The real challenge was determining what is the coefficient of discharge through that gap between the floating tube and the stationary tube, and after many tests in the lab, that was determined to be approximately 0.8. So now that we know how to calculate the flow through these buoyant flow regulators, let's talk a little bit about how we design them into our system and how we model them. How do we incorporate these things into our stormwater system design and then input the rating curve into our favorite hydrologic and hydraulic analysis package? The first thing you need to know is how to control the water level to get the most benefit from a buoyant flow regulator. And there are 2 ways to incorporate a buoyant flow regulator into a detention system design, both of which will save volume, but one will save a lot more. In the first case, case A on the left, the buoyant flow regulator's flow restriction is controlling the water level at the bottom of the detention basin. When you install the buoyant flow regulator like this, In this case, the water level in the basin must first rise to the point on the float where the device becomes buoyant before it will begin to discharge at a constant or nearly constant rate. Therefore, a certain amount, and sometimes significant amount, of storage volume is used up just to get the device up to its design flow rate. The better way to do it, when possible, is the second case, case B, shown on the right side of your screen. In here, the buoyant flow regulator's flow restriction is located below the level of the bottom of the basin, such that it's floating inside of the box. Note that in this case, very little to none of the volume in the storage basin has been used to get the device up to its design flow rate. When there's enough head available in the overall detention system to install the flow regulator in this manner, a significant amount of volume in the bottom of the system can be saved. For Thirsty Duck's products, this is typically anywhere from about 6 to 12 inches of storage depth. So anytime you can install this in a box below the bottom of the pond, you will always save more volume. So let's talk a little bit about the various types of storm event analyses and regulatory frameworks in effect around the country and how you incorporate Thirsty Duck into those designs. Where I live down here in Florida, stormwater system design regulations require that the post-development discharge can't exceed the pre-development discharge for the 25-year event. In the northern portions of Florida, it's the 25-year 24-hour event, while in the southern part of the state, it's the 25-year 72-hour event. When local regulations require analysis of only one event, design of the buoyant flow regulator is simple. You simply size it to produce the allowable outflow rate for the design event. And of course, the result will be a minimum of detention volume. However, in many states, the regulations often require analysis of multiple storm events, such as the 2-year, 10-year, and 100-year storms. When sizing a buoyant flow regulator for this type criteria, you almost always size it for the most frequent storm event and then design traditional weirs and orifices to control the discharges from the less frequent events. When the buoyant flow regulator is sized in this manner, it can never produce a flow rate which exceeds the allowable discharge for any of the required design storms. Now, of course, there's nothing that says you can't use a separate buoyant flow regulator to control each separate event, and we here at Thirsty Duck would really like it if you did that. However, pairing a buoyant flow regulator with traditional weirs and orifices is the most cost-effective way to do it, and you will still save quite a bit of storage volume when you do it in that manner. Out in Washington, California, and many of the other western states, stormwater systems are now being designed under the hydromodification regulatory framework, where continuous simulation and flow duration frequency analyses are required. Since flows which equal the threshold rate are generally considered to be an exceedance, the buoyant flow regulator should be sized to produce a rate just below the threshold. Our experience here at Thirsty Duck has shown that the rate should be about 2% less than the established threshold. In Western Washington, the threshold's been established at 50% of the 2-year pre-development flow rate. I'll add that that's in forested conditions pre-European settlement. That's otherwise known as 50% Q2. And in this case, the flow regulator should be designed to produce 48% of Q2 so as to avoid exceedances at the lower portion of the curve. Similar to the multiple storm event design shown in the previous slide, traditional weirs and orifices located higher up the riser are used to control the number of exceedances for the less frequent flows. So let's talk a little bit about inserting the rating curves for these buoyant flow regulators into your favorite software package. For the next series of slides, I'll show you how to model buoyant flow regulators in your favorite software package. And as you may have seen in our magazine advertisements, Thirsty Duck is now a HydroCAD supported product, and the good people over at HydroCAD have worked pretty closely with us to develop 3 different ways to model buoyant flow regulators in their software package. The first and simplest way is by choosing the constant flow / skimmer outlet option. When using this option, a buoyant flow regulator is modeled with an idealized 3-point curve, which assumes a linear transition from zero flow up to the design flow, and then perfectly constant flow thereafter. Using this feature is a very efficient way to quickly model the outlet to determine if any further or more refined analysis is required. When using this option, I recommend you use a phase-in depth of about 9 inches. The phase-in depth in HydroCAD represents the operating head for the buoyant flow regulator. If you're analyzing a fairly low flow system, less than about 1.8 CFS, you can also use the preloaded normalized thirsty duct rating curves, which are now built into HydroCAD. I think that's in build 13. These rating curves for all of the available orifice diameters and operating head ranges for our TDP series flow regulators. To access this feature, select the user-defined outlet option and then click Load File and select Thirsty Duct. All of the preloaded rating curves have been normalized to 5 feet of bellows extension. In other words, when you enter the design flow rate, you're entering the flow rate which should be achieved after the device has risen 5 feet from its resting position. For more detailed analysis and, of course, for final designs, HydroCAD also allows you to import a custom rating curve created with the Thirsty Duct Design Tools. You can download the Thirsty Duct Design Tools from our website. To use this option, select the user-defined outlet option and then select Load from File and navigate to the CSV file you generated with the Thirsty Duct Design Tools. This slide shows a little plot that shows the difference between each of the 3 modeling options available in HydroCAD. Here you can see that the constant flow skimmer option provides a reasonably good approximation of an actual rating curve, and that the normalized rating curve option produces a slightly conservative approximation of the actual rating curve. And again, for final designs, we always recommend that you use an actual rating curve generated with our design tools. For those of you out in Washington and some of the other western states that have adopted hydromodification, this slide should look pretty familiar to you. This is a screenshot from the Western Washington hydrology model. And if I didn't tell you it was the WWHM, those of you in San Diego or San Francisco would say it looks a lot like your hydrology model. All of the Clear Creek Solutions models allow the user to input a custom SSD or stage storage discharge table. The Thirsty Duct Design Tools that I talked about a minute ago include functions to generate custom stage storage discharge tables for import into any of the Clear Creek Solution hydrology models. If you're using an older version of the model, such as the WWHM3, you can import the SSD table in CSV format, and the newer versions of the model, such as the WWHM12, allow the user to copy and paste the SSD table directly into the model. For those of you here in my home state of Florida who use ICPR from Streamline Technologies, you can model buoyant flow regulators using the rating curves and operating tables function. First, create your own custom rating curve using the Thirsty Duct Design Tools, and then copy and paste the rating curve into ICPR. When modeling systems where the tailwater elevation is going to remain constant over the routing, select the Headwater X, Discharge Y option in the function box. And if you're modeling a system where the tailwater is expected to vary over the duration of the routing, select the Tailwater X, Headwater Y, Discharge Z option in the function box. When this option is selected, you'll need to generate a family or a series of rating curves at varying tailwater elevations using those Thirsty Duct Design Tools. Here you can see the screenshot on the left illustrates a single rating curve when the tailwater is assumed to remain constant, and the screenshot on the right shows a family of rating curves created at varying tailwater elevations when tailwater is anticipated to move during the routing. If the water surface elevation of the tailwater should fall between the curves, ICPR will interpolate between the curves to determine the flow rate. Many of you who are AutoCAD Civil 3D users are now using Autodesk's built-in Hydraflow Hydrographs feature. Modeling buoyant flow regulators with this package, it's a little bit more cumbersome than some of the others, but it can be done. You must first create your rating curve using the Thirsty Duct Design Tools, and then manually enter the rating curve in the user-defined discharge column on the Outlets tab, as shown here on the screen. Hydraflow Hydrographs only allows you to enter points at predefined, and this is important, predefined stages or elevations, so you can't just simply copy and paste the rating curve from the design tool. You must manually select and key in the flow at each of the predefined elevations. You'd think Autodesk could do a little bit better than that. For those of you who use PondPack by Bentley Systems, you can also model a buoyant flow regulator by adding a user-defined rating curve to an outlet structure. First, create a rating curve using those thirsty duck design tools, and then copy and paste the rating curve into PondPack. And it's important to note that rating curves in PondPack must start at the bottom of the storage volume, so it may be necessary to add some zero discharge points to the rating curve below the elevation where discharge starts in your design. This would typically happen if you had a detention basin that had some extended detention volume or BMP volume on the bottom before you actually started your discharge. For those of you who don't use any of the packages I just went through, hopefully you're getting the general gist of how you do it. If you're using SWIM or HEC HMS or BRN or some of the other packages that are available out there, you'll see that most software packages allow the user the ability of inputting some custom or user-defined stage, elevation, or head versus discharge relationship. The first thing you should do if you're using one of these packages is download a copy of those Thirsty Duck design tools, and then check your specific software user's manual for instructions on how to import the curve. And of course, if you can't figure that out, you can always feel free to call me here at Thirsty Duck, and I am happy to help. So for this last part of the webinar, I'd like to talk to you a little bit about what are some of the good and the not so good applications of this technology. Well, the first really good application, and the reason these things were invented, was for minimizing the physical footprint or land area required for the detention system. Keep in mind that when we talk about reducing the volume of a detention system, we're only talking about that portion of the system which is allocated for flood attenuation. In general, you can't use a buoyant flow regulator to reduce the volume allocated to water quality or BMP treatment. The amount of volume required for water quality purpose is typically a minimum set by some regulation, so it's not really possible to reduce it, otherwise you'd be violating that regulation. The next best application is reducing peak stage or design high water levels. Since volume is the product of both area and depth, if you keep the area constant, the result is that you will reduce the system depth when you use a buoyant flow regulator. Using the technology for this purpose can help to reduce the cost of import fill in low-lying areas, or it can be used to solve flooding problems in existing systems which maybe weren't designed with adequate capacity or before the current regulations. One of the most promising applications of the technology, and it's really starting to catch on, is using it to maximize water quality treatment or BMP volumes. Most stormwater detention systems have two parts. The volume in the lower portion of the system is typically allocated to BMP treatment, and the volume in the upper portion is used for flood or flow rate attenuation. Since the buoyant flow regulator can be used to minimize the amount of attenuation volume, this leaves more volume available, which can be allocated to BMP treatment. With more stringent nutrient reduction criteria and the implementation of TMDLs, this application is becoming more and more popular throughout the U.S. Here's one of the not so good applications, and this is a problem that we see almost every day here at Thirsty Duck, and we call it the bypass flow problem. Oftentimes when a civil engineer is designing the grading and drainage for a project, there are certain areas of the project where topographic limitations prevent the capture of stormwater runoff by the detention system. And when this happens, the engineer often needs to over-detain or over-control the runoff from the areas he can control so as to mitigate for the amount of flow bypassing the system. When it becomes necessary to over-detain, what you're really doing is creating a separation between the hydrographs, which represents the discharge from the detention system and the amount of the bypass flow. Since the total flow at the ultimate outlet from the project is the sum of both of these flows, then you want to separate the hydrographs so that their respective peaks are not hitting the outlet at the same time. Therefore, over-detaining the area which can be captured creates a certain amount of lag between the hydrographs. When you use a buoyant flow regulator to control the outflow from the detention system at or near the maximum allowed rate, this kind of becomes self-defeating. The purpose of over-detaining was to create some lag between the two hydrographs. When you use a buoyant flow regulator sized to discharge at the maximum allowed rate, it ends up negating the lag because it shortens the time it takes the detention system to reach its peak discharge rate. Now that doesn't mean just because there's some bypass flow that you can't use a buoyant flow regulator. It means that you probably don't want to design it to produce the maximum allowed discharge. You're going to want to size this for something less. Another solution to this problem is to raise the buoyant flow regulator a little higher on the outlet riser, which is another way to create lag between those two hydrographs before you start discharging at the maximum rate. Another one of the not-so-good applications for this technology is trying to minimize the area of a system that has a significant infiltration requirement. We see this quite a bit here at Thirsty Duck as well. The overall rate of infiltration is a function of the amount of surface area available for infiltration. So if you use a buoyant flow regulator to reduce the overall area of the detention basin, you're also reducing the amount of area available for water to infiltrate. As in the bypass flow problem, this doesn't mean that you can't use a buoyant flow regulator. It means that using it to achieve the absolute bare minimum amount of area may negatively impact the ability of the system to actually achieve its minimum infiltration volumes. And of course, this will be highly dependent on your local soil and groundwater conditions. Another common problem that we see here in Florida, and not such a good application, is what we call the low system flux problem. This happens in areas where the depth to groundwater is very shallow, and in lots of areas here in Florida that's as little as a foot. When detention systems are designed in these conditions, there's only a minimal amount of vertical storage available, and thus a minimal amount of head available to move the water through the system. When you use a buoyant flow regulator in these conditions, it'll always save a little more volume than the traditional Weir or Orifice, but it probably won't save that much more. When a detention system doesn't have much room to move, the buoyant flow regulator doesn't have a whole lot of time to do its job. All of the available head in the system is used up before it can ever get up to its designed discharge. And the last of the not-so-good applications I'd like to talk about is another common problem we see here at Thirsty Duck, and we call this the very high inflow to very low outflow problem. In many areas of the U.S., and ever increasing, the regulations have been enacted to reduce the discharge rate from very frequent storms, such as the one-year event, and the purpose of these regulations is to minimize discharges which may erode downstream channels. Since the discharge rate is very low compared to the inflow rate, there's not much minimization of the area between the inflow and outflow hydrographs that you can actually achieve. Think of it kind of like this. If the allowable discharge rate is 0.001 CFS and you could discharge that at a perfectly constant rate for 24 hours, the total volume you would discharge would only be about 86 cubic feet. That's not too much volume, and that's probably nothing to write home about now, and probably doesn't warrant using a buoyant flow regulator. Well, that's all I have for you today, and I'd really like to thank all of you for taking the time out of your busy schedules to participate in my webinar. I've enjoyed speaking with you, and I hope that you've taken some of the mystery and misconception away about this technology, and that we have some time for question and answers. So I've been shot at by the best of them, so go ahead and fire away, and I'll do my best to answer your questions.
All right, thanks, John. So I have just a few housekeeping items to cover before we start today's question and answer session. First, your feedback is important to us, so please take a minute to complete the short survey, which will pop up after the webinar is complete. Second, prior to the webinar, we emailed a link to the PDF of today's presentation. If you didn't receive it or are having trouble downloading it, please contact Zach at ztrafney@forrester.net. Third, the webcast version of this webinar will be available for your viewing. This full session is recorded, so if you missed any part of this webinar or would like to view it again, you may do so via the link we will email tomorrow. You'll be able to access this recording for 12 months. We will also be emailing certificates to those of you who stay the length of this webinar. If you do not receive a certificate, please contact Zach at ztrafney@forester.net. If you have joined us in a group with additional attendees who have already registered, please send your attendance form to Zach after the webinar. And if you have joined us in a group with additional attendees who have not yet registered but would like to receive CEU PDH credits, please contact Zach at ztrafney@forester.net. And with that, John, would you mind putting up the slide with your contact information and information on some of our upcoming webinars, including our Sediment and Erosion Control for Construction Sites Masterclass Series presented by Jerry Fifield and Tina Wills from April 22nd to May 29th, our Hydraulics 101 for those who skipped it in college webinar presented by David Williams on April 28th and April 30th, and our Permeable Pavement Masterclass Series presented by David Hine from May 21st to August 12th. And be sure to check out our on-demand library at foresteruniversity.net with over 150 webcasts. And with that, we'll open it up for questions. Our first question comes from David, and he asks, is there a way to backflow and flush these devices if they become clogged?
Well, first, David, let me say that for the last 4 years, I've had to travel to Minneapolis to the St. Anthony Falls Hydraulics Laboratory where we do all of the testing on Thirsty Ducks products. And you can't buy your way into the St. Anthony Falls lab. You have to go there, and your research has to be for a public purpose. And it was requested that we go there at the behest of the Florida DOT and the Minnesota DOT. The Florida DOT gave the laboratory instructions to throw as much debris at Thirsty Duck as possible to try to clog it, and I'm happy to report to you that in 4 years they've never been able to clog a Thirsty Duck. Now, I'm not dumb enough to tell you that one could never clog, but they haven't been able to do it yet. And the reason for this is actually fairly common sense. When you design a traditional static orifice, you're designing it for a fairly high head condition, which, if you remember, the orifice equation is a function of both head and the area of the orifice. So for any two equivalent flows, if you have high head, the area of the orifice will be smaller than a system which operates at low head. Thirsty Duck operates at very low heads. That's why it can get up to its peak flow rate very quickly. So the area of its orifice is typically on the order of 4 times larger than what you would have designed if you had designed a traditional static orifice. To answer your questions about backflushing, of course, if you can access the outlet and you can force water backwards through the Thirsty Duck, you could use that method to potentially clear a clog. However, we do make that very easy for you. There's actually a 4-inch access hole on the top of our TDP series flow regulators, which you can reach down through, and if there is something clogging the orifice, reach in and pull it out. And on our ER series flow regulators, there's a hinged grate on top, which if there's something clogging that orifice, you can simply open the hinged grate, reach in, and pull out whatever may be clogging it.
All right, great question, David. Thank you. And a lot of people are asking about the use in cold weather. So how do the Thirsty Duck products work in cold weather places, and do the installations stand the test of time with temperature, ice, and thaw over several years?
So far, so good. Keep in mind that Thirsty Duck is typically designed to control the outflow for that portion of a stormwater system which is allocated for flood or flow rate attenuation, which means it's up above that water quality or BMP volume. That means that Thirsty Duck's floats are typically sitting up above the normal water level in a detention system so that they are not exposed to ice. We have found out in the lab that if a Thirsty Duck, a Bellows type Thirsty Duck, our TDP series, are exposed to ice, where ice gets around the bellows, that repeated cycles of freezing and thawing can cause some pressure against the bellows, which can deform some of the reinforcing rings inside of that bellows. When we install a thirsty duck in freezing conditions where its bellows could potentially be exposed to ice, we substitute a section of the bellows for a rigid aluminum tube, very thick rigid aluminum tube I might add, so that the pressure of the expanding ice around that tube can't collapse the tube. And of course the best way to protect the bellows from freezing is to install it in a manhole, and I will tell you that most thirsty ducks are installed in manholes where they are out of sight and out of mind.
All right, well, thank you all for asking about the cold weather. And we have a question in from Jane. She asks, how big is the gap between the inner tube and the outer tube?
That's a very good question. The gap is not uniform. Typically the tubes are rectangular rather than square-shaped, and on the long side of the rectangle we'll leave the gap at about 1/2 inch, and on the short side of the rectangle we leave the gap at a minimum of 2.5 inches, and let me explain why. In the United States, a standard aluminum beverage can has a diameter of 2 3/8 inches. So if we leave a gap of at least 2.5 inches on the short side of that rectangle, then cans and plastic water bottles and the like can pass through the device without fouling it. On the long side of the device where we leave the gap at 1/2 inch, that's enough to provide adequate flow restriction, but still enough gap to let small pieces of debris like small twigs, sticks, cellophane wrappers, and the like, leaves especially, through without clogging it.
All right, great question. Thank you, Jane. And a follow-up question from Kirby. He says he would have expected you to use the sharp edge Weir equation rather than the broad edge. Could you please explain?
We did a lot of testing to determine Weir and Orifice coefficients in the laboratory, and as I said, our testing determined it to be closer to 3.2. I would tell you this, one of the things that we learned in the laboratory is that measuring flow is not a simple science, especially when you're doing it at flow rates of 10 and 20,000 gallons per minute. Flow metering is typically done with measurement weirs, which have to be calibrated each time they're used, and the accuracy of that calibration and the accuracy of those measurements changes a little bit from experiment to experiment. Interestingly enough, I think the flow coefficient for a sharp-edged Weir is 3.13 versus 3.2 for the broad-crested Weir. So when you're measuring very, very large flows and very small changes in water surface elevation over that measurement Weir, those types of differences are very difficult to detect.
All right, thank you, Kirby. Great question. And we have a question in from Jimmy. He asks, can the float or Weir or Orifice be configured to provide skimming of the surface water, and if not, can an oversized pipe be placed around the thirsty duck to be utilized?
Jimmy, that's a very good question, and no need to worry. All of the thirsty duck products are self-skimming. I didn't really, because I was trying not to make this so much an advertisement for Thirsty Duck, more as an educational webinar, I didn't really go through the pieces and parts of each of their assemblies, but the Thirsty Duck TDP series, which is a Bellows type buoyant flow regulator, has a shroud which covers its flow restrictor so that it's self-skimming, and that shroud or floating body, if you will, extends at least 12 inches below the opening of the flow restrictor. And then in the ER series, which are concentric tube type flow regulators, in order for a float to be buoyant, that means it is displacing water. So a portion of that float is always below the water surface. So water has to flow down and under the float to actually get to the flow restriction. So the floats themselves provide skimming. In the gaps between the floats, we add an aluminum debris shield between them to provide skimming on all four sides of the device. So no need to do any special modification or installation for debris skimming.
All right, great. Thank you, Jimmy. And we have a question in from Amit. They ask, what are the major maintenance problems with the system to be aware of before specifying it?
I get that question all the time. And the honest answer is I don't know. The first thirsty ducts were installed in Bellingham, Washington in 2004, which is now 11 years ago. And so far they have been working flawlessly. No maintenance has ever been required, and they have never clogged. And the first ER series, or concentric tube type flow regulators, were installed here in Florida back in 2010. So we're now in our 5th year of operation with those. So far we haven't had to do any maintenance, and I'm not dumb enough to tell you that no maintenance might ever be required. However, they're fairly simple devices, and there's no friction, if you will, in their operation. There are no mechanical parts which rub up against each other that could wear out, other than maybe painting as the aluminum gets scratched up over the years. That would be about all of the maintenance I would expect. I do recommend to my customers that they periodically install their inspect their thirsty duct installations after large rainstorm events to make sure there's not an accumulation of debris or a log or something that's gotten caught in one of them. And so far I haven't had that happen.
All right, great question. Thank you, Amit. And we have a question from Bill. He is wondering how long the Thirsty Duck product has been in use.
Oh, okay, Bill. As I said in the answer to the last question, the Thirsty Duck TD series was first put into service in Bellingham, Washington in 2004. So that's coming up on 11 years now. And the first Thirsty Duck ER series, or concentric tube type flow regulators, were installed in Florida in 2010. So they're in now their 5th year of operation.
All right, great. Thank you, Bill. And another question from Jane. She asks, have any of the configurations obtained in an equivalent technology rating from the WSDOE?
Oh, I assume WSDOE is Washington State Department of Ecology. The Thirsty Duck is exempt from the Washington State DOE's TARP and TAPE programs. These are not BMPs, although we like to think they're best practices, but they're not a water quality device. Thirsty Duck is not intended to clean water or remove sediment or nutrients. They're simply intended to regulate flow. The Thirsty Duck has been seen by the Department of Ecology. They are very aware of its use, and they allow its use. And if you'll email me after this presentation, I'll be happy to provide you with a copy of a letter from Doug Howey over at the Department of Ecology indicating that it can be used in Washington.
All right, thank you. Great question, Jane. And we have a question from Jeffrey. He asks, have you ever applied your device in the New York City area for controlled discharge from a building tank? He says new regulations are pushing discharge flow rate design under 10-year conditions to 0.25 CFS.
Jeffrey, how would you like to be the first? I have not yet installed one for that application in New York, but I would love to take a look at your particular situation and see if we can apply Thirsty Duck technology successfully to that problem.
All right, thank you, Jeffrey. We have time for a few more questions. We have one from Mark, and he asks, if you put the device in a well below the bottom of the pond, how do you control sediment in the well?
You periodically would need to clean the sediment out of a well if you put it below the level of the bottom of the pond. I'm not sure, depending on how big that well is, how often you would have to clean that out, but clearly sediment would accumulate in that lowest point, just as it would on the bottom of a detention basin. And that, of course, will depend on the sediment load coming into that stormwater system.
All right, thank you. And Timothy asks, can this device be used in conjunction with a backflow valve to control surcharges in a combined sewer pipe?
Yes. Yes, the answer to that. We have a lot of customers who are trying to use Thirsty Duck in combined sewer applications.
All right, great. Thank you, Timothy. And a question in from Richard. He asks, what is the life expectancy of the device?
That's a good question because I haven't lived that long yet. I would tell you that the Thirsty Duck ER series is fabricated from aluminum and steel. In order to get the Florida DOT certification, their materials engineers had to be comfortable that the design life of the product was at least 50 years, and they have given us their blessing. So we'll go with at least 50 years. On the Thirsty Duck TD products, those are fashioned from linear low-density polyethylene, which should last a lifetime. It is UV stable, so you shouldn't have much problem with sunlight breaking that plastic down over time. However, most Thirsty Duck TD series are installed in a manhole where they're not really exposed to UV light anyway.
All right. And one last question from Joseph. He asks, where did the Thirsty Duck name come from?
That is a very good question, Joseph. Adam Fulton, who is the inventor of the Bellows type buoyant flow regulator out in Bellingham, Washington, was very excited about his invention, and when he found out he was going to get a United States patent for it, he was telling his wife, and his wife is a non-engineer, and as he was trying to explain what the Thirsty Duck did, she wasn't quite getting it. Adam got a little frustrated with her, and he said, "Oh, honey, don't worry about it. All you need to know about this thing is that it drinks water fast." And she responded, "Oh, like a thirsty duck." And so that's how the product got its name.
All right, great to know. Thank you, Joseph. And that concludes today's question and answer session. If we didn't get a chance to answer your question during our session, we will follow up via email. And with that, John, do you have any final comments for today's audience?
Just to say thank you. Again, I'm honored that so many of you would take time out of your busy schedules to be with us here today. And if there are questions or comments that you didn't get answered here today, please feel free to call or email me at the address shown on your screen, and I will be happy to help you. Thank you.
All right, thanks, John, and thank you all for joining us today. And thank you to our sponsor, Thirsty Duck LP. Thirsty Duck LP is the global leader in buoyant flow control technology and provides custom configured flow control solutions for a variety of civil and environmental engineering applications. Thirsty Duck's innovative flow control products have saved millions of dollars in land and construction costs for both public and private sector clientele. And we hope you can join us for some of our upcoming webinars, listed including our Sediment and Erosion Control for Construction Sites Masterclass Series, presented by Jerry Fifield and Tina Wills from April 22nd to May 29th, exploring the ins and outs of effective sediment and erosion control plan design and review for construction sites. Our Hydraulics 101 webinar, presented by David Williams on April 28th and 30th, exploring the concepts, terms, and analysis behind hydraulics and the basis of the analysis that goes into hydraulic studies. Our Creating Your Sustainability Plan webinar presented by Antonia Graham on May 12th, exploring the step-by-step of how you can build your sustainability plan for success, and our Permeable Pavement Masterclass series presented by David Hine from May 21st to August 12th, exploring permeable pavement design, construction, and performance. Until next time, thank you and have a great day.